Good morning to all of you. Hello, this is me, Arfat Firdous, and today I'm going to continue my discussion that I have had yesterday, in which I was talking about the creation and annihilation operators. In general, we call them as ladder operators. And yesterday we actually tried to demonstrate mathematically that how you can write down the Hamiltonians in the two frameworks, and how you can achieve some of the important results from using these action operators. And again, I would like to start my argument with an infusion of realizing that we are doing science, and science science is certainly something that gives us an insight about the nature of reality, how nature behaves, how nature reacts, and maybe at times the nature is dictating us to copy its actions, and at the same time nature is restricting us to completely understand it. So what we have been talking about is, here we are talking about these operators, creation and annihilation operators. These names does not suggest that you are actually annihilating something. Here the meaning goes with the logic of taking your quantum mechanical system from one state to another state. So here you are not interested in the motion of the particles, you are interested in the state of the system, that how your system, what's the structure of the system, and how system is dictating, is being dictated by an action that's being imposed on that state of the system. So again, I would like to tell you that as Arfat Firdous, what am I trying is, I'm not trying to teach you. I'm trying to learn. Basically, I'm trying to share the things that I feel that I should share with you. And at the same time, I want to be sure that you are at the verge of completion of the syllabus for the semester 7. So basically, I'm talking to the students of the semester 7 who are at home, enjoying the breeze, enjoying the cold, and I'm here delivering a lecture on creation and annihilation operators, and I hope sitting at home they can take some benefits from this interaction that I have. So maturely speaking, what I'm trying to tell you is that we are not here interested in how the things are moving. We are interested in we are moving from motion to the symmetry, and we are moving from trajectory to the structure. We are moving from complexity that we can see in resolving the Schrodinger's wave equation to the simplicity. That's the argument. So the point is, yesterday what we did is we had those Hamiltonians, and what one was H equals it was H bar omega times a dagger minus 1 by 2, and in another case we obtained H bar omega a dagger a minus 1 by 2. Okay, these equations are very helpful in demonstrating actually the mathematical staircase of the quantum mechanical system, because when these action operators are acted on the quantum state, they either shift that quantum state to one step ahead, or it lags down the quantum state a step one step behind. So this forward and reversal we would like to see in the mathematical framework, in this mathematical argument. So to start with, what we are going to do is we would like to see basically first that if I use this A dagger, what we call as this A dagger is termed as the creation operator. So it's a creation operator, or you may call it a creator operator. And this A dagger, we would like to see mathematically how this A dagger will shift the system by 1 unit. So when we talk about the unit here, the unit certainly will mean the packet of energy, and the packet of energy is something what's called as h bar omega, that's reflecting in the Hamiltonian here. So this is the packet of energy, and the shift in the energy should be resolved in the form of 1 unit adding to the original energy of the system, or the system should go back by a unit as h bar omega. So this is something that we would like to realize in algebraic structure. So I have these two equations. I may call this equation 1, equation 2. I don't know, I may have to come back for this equation. So what's the first thing that I want to demonstrate here is that if I have the Hamiltonian, and this Hamiltonian is reflected upon a creation operator, and this whole thing is acting on say the ket of psi, okay, and this certainly will lead me to the energy eigenvalues. I may call it E dash of psi. So this can be a mathematical argument that we will have right now, and we would like to see that where we can reach as we proceed from this simple equation. So if I think of using h here, as h bar omega times A dagger A. So A dagger A, and here you will have plus 1 by 2, and this will act on A dagger and the state psi, and this will lead us to E dash of psi. Okay, the point is that we want to see what actually this creation operator is going to do with this eigenvalue equation that we have written down. So we can see here, I would like to first of all incorporate this A dagger in this bracket. So if I do it from left. Okay, it's from me, with respect to me, it is from right, so I'll move this inside. So when I move this inside, I'll get h bar omega, so you'll have A dagger, A, and then you will have A dagger. So here you have your original plus 1 by half, and then you are with the state psi, the ket of psi, treating E dash of psi. Okay, now what I can do is I incorporated this A dagger from this side into the bracket, but at the same time, okay, I'm missing something. Here I have to put this A dagger because I'm incorporating this A dagger in the bracketed term. So what we can see here is in the left of the terms that are in the bracket, I can have this A dagger outside the bracket. So I can do that. So what I'll achieve from doing that is I will have A dagger out, and then I will have h bar omega, and inside I'll be left with A dagger, and then I have plus 1 by 2, and then the ket of psi leading us to E dash of psi. So this should be the case. Now we can see that I would like to incorporate this packet of energy into this bracket. If I do that, I stand back with this creation operator, and inside the brackets what I will have is h bar omega, then a, and then a dagger. Okay, this thing will be there, and this h bar omega will lead me to h bar omega by 2. Okay, then I'll close in, and that will be my E dash of psi. Okay, now looking for this part of this bracket, I can obtain this part from the equations. This is a dagger part. So if I see that equation in which I have a dagger, so this is my equation. This is h bar omega a dagger. That must be equal to h plus h bar omega by 2. So I'll be using that. So it's going to be h bar. So here I will have a dagger, then you will have the Hamiltonian h plus h bar omega by 2 plus h bar omega by 2 and psi, and this is going to be equal to, so this is half plus half, this is going to give us 1, and this h is our original Hamiltonian, so this h is going to give me E. So what am I going to get is, I'm going to get a dagger E plus h bar omega of psi equals E dash of psi. So what does this equation reflect here is, this equation is reflecting that acting this creation operator on the Hamiltonian will lead that Hamiltonian to be shifted. It will lead that Hamiltonian to be shifted from energy. If the corresponding energy of this Hamiltonian is E dash, it is going to reflect the Hamiltonian as E plus h bar omega. So there is a packet of energy is added. It's not the half of the packet. You are moving mathematically in this mathematical universal space where you have to exactly take a step of energy. You cannot take a half step. You cannot take a quarter to the step. You cannot take 1/3 of the step. The step has to be only 1. It has to be 1. And that's what we are trying to understand from here. That means the creation operator is taking the energy of the system ahead by a packet of energy. And the same rule, the same mathematical strategy can be applied in resolving the annihilation operator. And annihilation operator, you will be choosing same kind of equation. Then this annihilation operator will take the energy of your system by E minus h bar omega. So confirming the results that we obtain using the tedious calculations, solving Schrodinger's equation and solving those differential equations. And here, copying nature directly leads us to the set of quantization, the steps of quantization that are the backbone of the microscopic world. And at this point of time, we cannot say that classical, see, most of the times the argument that we play is the classical physics, it's a failure of the classical physics. Basically, we should not use the word failure. The classical physics is not a failure, it's a beautiful physics. Everything that's happening in science, in the macroscopic world, even from Newtonian gravitational perspective, you are able to shoot your satellites, using those simple gravitational equations and the equations from general theory of relativity. So what am I trying to tell you is that you are trying to go towards a more precision. You are moving towards the more fundamental understanding of the nature. You are going a step ahead of the classical physics. That can be an argument. You are moving a step ahead of the classical physics to understand the true nature of the cosmos, the true nature of the universe, the true nature of the things that we are being built of, the true nature of everything that surrounds us and that's within us being created. So the point is, so this was the first argument that I was trying to cross upon. Now the second thing I would like to talk about is if I choose now a state, say for example, I choose this dagger on the state k, because the state has to be shifted by 1. So if I'm acting this dagger on k, it will lead this k to some number, or maybe a complex number. Let me call it a star or an star, and it is going to change my system to a ket of k plus 1. So this is the reality of the creation operator. And at the same time, if you make use of an annihilation operator on k, it's going to decrease the state of the system by 1. That's the case. But before we proceed on, it would be right for us to actually calculate this normalization for this equation. So how we can do that, how we can achieve this star, how we can achieve this an. Finally, when you take the inner product of the two states in ket-Bra notation, you have basically the multiplication of a number and its complex conjugate. So an, it has to be, I will call it an, but once you shift from the ket notation to the Bra notation, this an has to be written down as a star. And then when you take the inner product between the two, it will lead us to the mod of an star. So what am I trying to tell here is, this is my equation, and if I write down the Bra notation for this equation, that's going to be, for the dagger, you will get a simply, and then I think this is not the way I have to write it. So this will be for k, I'll have k here, and for a dagger I will have a here, and corresponding to this we will have k plus 1, and for an I will have an star. So this is our equation in terms of the ket, this is our equation in terms of the Bra, and between these two equations I can take the inner product. And we understand the inner product we have talked about the inner product of the kets and Bras a lot of times. So here I'll be writing down that inner product. So what will be that? So that will be Bra of k, and here you will have a cap and a dagger, and then you will have k. And in the right hand side of this equation, what you will have k plus 1, you will have k plus 1, and then you will have an star, then you will have an, and then you will have k plus 1. Okay, this is what you expect from taking the inner product of these two states, the ket states and the Bra states. And what we can have here is we have a dagger, and I think I wrote down the Hamiltonian in which I have a dagger. So what was that? In that case, H was H bar times A dagger minus 1 by 2. I think I must check it. For A dagger, come on. For A dagger, I have to go back, and for A dagger, yeah, for A dagger. This is the problem with this board. So for A dagger, this is minus 1 by 2. Oh no, this. For A dagger, this has to be minus. Yeah, it's minus here. I think here I have committed the mistake. This is plus. So if this is minus, yeah, it has to be minus. Maybe I have committed the mistake. I don't know. I'm not sure about that. But you can have an idea at least, and then you can refine the mistakes I will commit. And I think the mistakes that I will commit will teach you. You will not learn from clarity always. You will be learning from the mistakes. So what we are going to have here is, so this is minus half, okay? So from this, I can have H bar omega A dagger. This will be equal to H plus 1 by 2. Okay? And A dagger will be 1 by H bar omega times H plus 1 by 2. So this part, A dagger of this equation, I would like to replace this A dagger by this argument, 1 by H bar, H plus 1 by 2. And then, so 1 by H bar omega times H plus 1 by 2. And here you have the cat of K, and here you have the bra of K, and there you have A star, AN star, AN, and you will be inside with K plus 1 and K plus 1. So this immediately is equal to 1. We understand all that story from Chronicle Delta, and this K plus 1 will lead us to 1. So the right hand side of the equation will be the magnitude of AN squared. This will be the right hand side of the equation. Now let's go into the left hand side of this equation, see what happens here. I would like to separate out the two. So this is K, so this is 1 by H bar omega times H, okay, then plus, okay, am I doing it right? I think I'm doing it right now. So then this is plus 1 by 2 H bar omega. Okay, I will close it with K. And this thing is equal to, A n squared. Okay, so what do we expect here? Is we can separate out them. This is K times H by H bar omega with the K, and plus this is 1 by 2 H bar omega That's correct. Okay, so here you will have the cat of K and the bra of K leading us to AN squared. Okay, what do we expect from this Hamiltonian acting on K? What do we expect? We expect it to be En. Now, so this H will give us En. But what is En? En is E plus H bar omega. So this is, so everything else is out. This is K and K is out. So you have E plus this will give us E plus H bar. Come on, come on. This is H bar, omega, and this is H. Now this will give me E. So this is K and K, this is AN square. Something is happening. I'm not sure. So this is very easy, but I'm stuck. I'm looking for it. So this is H. If I go with H bar omega by 2. Yeah. And no. Okay, come on, yes. I'm committing that mistake. Yeah. This H, when this H will act on this K, what it will lead us, in harmonic oscillator problem, it will lead us to E plus 1 by 2. This is what it's going to lead us with. E plus 1 by 2. That's it. But here I am missing something. So this will be, yeah, okay. So what this will be N plus 1 by 2 E. This was something that I was missing. So H acting on K will lead us to N plus 1 by 2 E. So if that is the case, what we are going to get from here is 1 by H bar omega will be out. Let us see, I don't know. So 1 by H bar omega will be out. Okay, what will be inside? What will be inside will be N plus 1 by 2E. Inside will be N plus 1 by 2 times E. Okay, N plus 1 by 2 E. Here I want to check this part. This part, this is 1 by H bar omega. It's for the whole. Huh? It is for H plus 1 by 2. Okay, that's right. Let's see. Okay, then plus 1 by 2 H bar omega is A and star. Okay, what is it that I have messed up? I have, this will give me, if I put this as, but that will not work. If this is H bar omega, if this is H bar omega now for E, then this H bar omega and H bar omega will go, but I have somewhere I have committed the mistake. This H bar omega should not exist. So you will have to check that, because I cannot resolve it, then I have to go back. You can resolve it. So this h bar omega should not exist. So what should exist? This E should go in terms of h bar omega. You will be left with n plus 1 by 2 plus 1 by 2 equals an squared. So certainly I have committed a mistake somewhere, and I want you to resolve that mistake, and it will be a very good exercise for you to work on, because finally you will get rid of these h bar omegas and you will be left with this 1/2 and this 1/2. You add the two, that will give me n plus 1 equals an squared. So this an can be written as, since we started this discussion on a creation operator, so this an will be under root of n plus 1. So that means if I am using a creation operator, say a dagger, on the state K, the result of this state will be under root of K plus 1, and then you will have the state, K. Right. And this is for the creation operator, and for the annihilation operator, you will automatically find, if you act this on a state, the quantum mechanical state K, it will lead you to under root of K times, this has to be K plus 1, okay, times K minus 1. Okay, this is the result that we wanted to ensure. So that means the two results we have tried to obtain. In first case, we realized that your quantum mechanical step has a step of energy addition as h bar omega, or the energy reduction as h bar omega. So everything is happening like staircase. It's not acting something continuous in the nature. So the nature is responding in a way as if it's a stair. So that is the case when you talk about the energies. And then we try to analyze these creation and annihilation operators, acting on quantum states, acting them on the cats, and realizing that the quantum state, when you act a dagger on a quantum state, your quantum state raises by the number 1, but at the same time you have to ensure the normalization constant. It was that normalization constant that we were trying to calculate, and something happened there, but I have put down that problem in your hands. You will resolve that h bar omega should not exist. You should get that equal to n plus 1. So what's happening here is you have a creation operator acting on K, leading you to a state K plus 1 with a normalization constant under root of K plus 1. If you have the annihilation operator, what it does, it takes your system one step down, and at the same time you are introducing the normalization constant. This is how these beautiful results go on in demonstrating the different fields of physics, demonstrating the quantum field theory, demonstrating the nature of light in quantum field theory, and having tremendous applications in condensed matter physics and in modern scenario of physics. So that's it for today. I hope you enjoy it. I hope you like it. With this, I would like to say you goodbye and have a nice time. Bye.